So what do we come up with? What is one way that a population grows, or why a population would grow? Yeah. The lack of a predator, right? A predator being something that eats it, right? Would cause it to grow. Okay. Angel, did you have a different one?
Oh. I thought you were talking about like humans.
Yeah.
So I was thinking poverty.
Poverty would be a cause for populations to grow, or
Yes, growth.
okay. Could you explain a little bit?
So we saw this video on AP Hub today that poverty is a cause for population growth, and if you see the data, the wealthy and the healthy people usually have like 1 to 2 children.
Mm-hmm.
So countries like developing countries such as India and around there, Southeast Asia, they usually have a lot more children in their families, and it's usually in an area where it's not very wealthy. So basically, in order to stop population growth, you need to have health care for children. That makes any sense. I probably doesn't make any sense.
Okay. Well, thank you for sharing that. It's really interesting. I hadn't thought about it in that way. I think the question that comes up for me is it a correlation that just so happens that poverty is associated with having more children, or is that a causal relationship, meaning one causes the other? So we won't get into it now, but thank you for sharing that. That's something to think about. Okay, so we got Angel has shared. We also heard that lack of predator. So let's think about animals in this case. What's one more leaf of a reason a population could grow or decline? Abundance of food. Yeah, absolutely. So on our notes, what we're going to do is I'm going to talk about a couple of key principles that we're going to draw from. If you remember from explanations, we need that scientific theory or principle for explanation. So at the top here, our first key principle. This is going in your notes onto page 15. Key principle number 1. All populations have the potential or the ability to grow exponentially. Under ideal conditions. Okay. I'll show you exponential growth in a moment. But all populations, whether it's honeybees, humans, rabbits, bacteria, have the ability to grow exponentially under ideal conditions. Now, what do I mean by ideal conditions? Well, you already mentioned some. So, ideal conditions include infinite resources, food, water, infinite resources, no natural disasters, right? So stable environment, no natural disasters, and no competition. Which kind of goes along with infinite resources. There's no competing or fighting over resources. All right. So we're going to be looking a lot at different graphs today. In terms of exponential, and I recognize that term from math class. So exponential growth looks something like this. So we have an x and a y axis, I'm going to have my population size on my y-axis. I'm going to have time, let's say in years, on my x-axis. Okay? So this is a population graph. Exponential growth looks like this. So as time goes on, the rate that the population is increasing gets faster and faster and faster, right? As opposed to something like this. This is what we would call linear growth. Whereas this is exponential growth. Okay? So every population has the potential to do this if they're in ideal conditions. They'll grow exponentially. Okay. Key principle number 2. So we know that ideal conditions they rarely exist. Or if they do, they rarely last. Okay. As a result, limiting factors prevent exponential growth from happening or continuing. All right. So, obviously our phenomenon of calling collapse disorder, we're going to be thinking a lot about this second key principle. What is causing, in this case, B's to decline? What limiting factors might be present that are causing that? So, our limiting factors, when we start investigating, we're going to think about it in 2 ways. So, there are 2 types of limiting factors. What's known as density dependent or density independent. Density dependent or density independent limiting factors. All right. So a density dependent factor, we say it affects a population growth, affects a population's growth more when when the population is more dense. So this limiting factor will affect a population more when the population is more dense. You can imagine density independent. This affects a population's growth equally, regardless of how dense the population is. Right? So one depends on how dense the population is, and one does not depend on how dense the population is. All right. So you might be asking, what do I mean by population density? So density is equal to the number of population members divided by the area that they occupy. So how dense a population, we can measure the density in this classroom by counting up how many people we have in here and dividing it by the area of our classroom. That would be our population density. Okay. So whenever we compare population densities, it's usually important to compare the same area. That way we can compare how dense they are. So, for example, if these two areas are the same, and a purple dot is going to represent a population member. And let's say in this area, that's our population. But in this area, that's our population. So we would say that this one on the left has a high population density. Another one has a low population density. Okay. So to wrap this up, if we think about this, a density dependent factor is going to start affecting a population when it gets more and more dense. A density independent factor is just going to affect both of these populations equally, doesn't matter how dense they are. So some examples. So for density dependent, there are three major examples we need to be familiar with. So the first one is competition. Second one is predation. And the third one is disease. Competition is fighting over limited resources like food, water, shelter. Right? So it makes sense that competition is going to start affecting a population the more dense it is, right? Because if the resources are limited, the more people or more members of the population you have in an area, the competition is going to increase, and that's going to start limiting the population. All right. Predation. So predation is when a predator consumes its prey. So if you're considering from the perspective of the prey, right? If you have a higher density, then predation is going to start affecting your population more because there's more prey around to eat, right? And so your population is going to start to decline a lot faster. And then lastly, disease. So disease can spread quicker in high density areas. Right? That's why in a few months, when the flu starts coming around, because the school has a high density, people are going to start getting sick. Right? It spreads quickly when there's a high density of people, or in this case, high density of any population member. All right. So, a density independent factor. There's three major ones. So there are weather changes, natural disasters, and bad human impact in the case of other species. So again, these affect a population regardless of if they're dense. So by weather changes, I'm talking about seasons. So for some organisms, certain seasons they fare better than others. But it doesn't matter if they're a dense population or not. It's just the seasons are causing this limit to their population growth. Natural disasters, like a flood, a hurricane, etc. And then bad human impact would be something like pollution or destruction of habitats. Okay. Again, it doesn't matter how dense the population is. The population is going to be limited regardless. Okay. So, why do I bring this up? When we start investigating, not only are these terms typically used a lot, but they're also helpful for understanding what might be going on that's causing colony collapse disorder, causing the honeybee population to decline. Okay, so we're going to reference this throughout the unit, but I wanted to give you these right off the bat. Are there any questions for me or things I need to clarify? Okay, so we're going to take a 3-minute stretch break. So if you need to get up, go to the bathroom, you can do so.